Hello everybody, Mr. Lake here with another chemistry video. We are continuing with our unit on stoichiometry, but we're actually ready now to start using some stoichiometry. Now that we know how to balance equations properly, we're ready for the next step. Now I want to just remind you that so far, really, in the last week or so, and we've been doing all this dimensional analysis and unit conversion stuff, I've really just taught you two moves, if you will. I've taught you how to go from particles to moles or moles to particles using Avogadro's number. And I've taught you how to do grams to moles or moles to grams using molar masses from the periodic table. And we also talked about how that can be complicated because if you're working with a molecule, you have to figure out the molar mass by adding up all the molar masses of the things that make up the molecule. But we practice that. It's really not too difficult. So again, there's only really two moves that we have covered so far in dimensional analysis. And stoichiometry, or using mole ratios, is just one more move. It is something else that you can add into a dimensional analysis, unit conversion, calculation, where you are now converting between substances in a balanced chemical reaction using a mole ratio from a balanced chemical formula. Now, it's not actually just unit conversion. It is something different because we're not just converting what unit is measuring what. We are actually like predicting how much of a product will be formed from the amount of a reactant. It's slightly different in terms of meaning, but mathematically, it's just another ratio conversion factor that you can use in one of those conversion problems that we've been doing. So today, we're really just going to be focused on how to use molar ratios in simple one-step conversions. But just know that because this is yet another tool, it is the third move that I've taught you, pretty soon we're going to start combining those moves. We're going to start combining molar mass and mole ratios, or maybe even mole ratio and molar mass and Avogadro's number, or maybe a mole ratio with the molar mass of both of the compounds involved. We'll get to that. I just want you to know that it is going to get more complicated, but we're going to start simple today. So the basic steps are pretty, there's no surprises here. First thing we're going to do is make sure that we are working with a balanced equation. Then we're going to make sure that we have identified all of our variables, what we know, what we want to know, and what conversion factors we think we might use. And then we're going to solve. So, first example. I tell you what, I'm going to stop. I'm going to pause. I want you to pause the video. Try to solve this on your own. Hit play when you're ready. Hopefully you gave it a shot. Whether you did or did not, let me walk you through this as an example. The question says, how many moles of H2SO4 can be produced with 12.5 moles of SO2? So very quickly, just kind of identifying what's going on, we want to know how many moles of this product can be produced with 12.5 moles of this reactant. So we know that we have 12.5 moles of SO2. We want to know, our goal is to know how many moles of H2SO4 we are going to use. And the conversion factor that we might use to get there is probably going to be something involving the molar ratio between these two things. As always, we start with writing down what we know in the upper left-hand corner of a conversion box. Just like before, what you can do is you can look at the units of what you know, and you can just write those same units down here. Because we want to get away from units of moles of SO2, and we want to introduce moles of H2SO4. And look at this, we have moles of one thing over moles of another. That's a mole ratio. We're going to take that from the balanced equation. And the ratio is for every 2 moles of SO2 that is used, 2 moles of H2SO4 is produced. So the answer is going to be numerically 12.5 times 2 divided by 2, which will equal 12.5. And units-wise, moles of SO2 gets canceled out. Moles of H2SO4 is what we're left with. And that's what we want to know. So that's a very simple example of how to use a mole ratio to convert from one thing to another. Now, it might seem like, why do we even do that? We ended up with the same number we started with. But actually, we didn't, right? We changed the units, which is just as much a part of the answer as the number. And also, we proved that, or we used mathematical evidence to show why we ended up with the same number. So just because a number doesn't change doesn't mean that there is no use to a calculation. Let's do something a little bit more interesting. Methane and sulfur react to produce carbon disulfide. How many moles of CS2 and H2S are produced if 1.5 moles of S8 is used? I'm asking you to do two different calculations here, one for CS2 and one for H2S. In both cases, what you know is that you have 1.5 moles of S8, and your goal is to figure out how many moles of that other thing you're going to have. So, give this a shot. I will disappear. Press play when you're ready. Here we go. First of all, we're going to figure out how many moles of CS2 would be produced from 1.5 moles of S8. I'm actually going to make those disappear so that I have a little bit more room to work with. So for the first one, we know that we have 1.50 moles of S8. I wish there was a way for me to make this pen a little bit smaller. Maybe there is and I'm just dense and don't know. Anyway, doesn't matter. Since moles of S8 is up there, we're going to just take that and put it down here. And we're trying to figure out how many moles of CS2 that will produce. The molar ratio of S8 to CS2 is that for every 1 mole of S8, 2 moles of CS2 will be produced. 1.50 times 2 is going to be 3.00. And units-wise, moles of S8 gets canceled out, and we're left with moles of CS2. That's how many moles of CS2 will be produced from 1.50 moles of S8. Now we can start with the same exact reactant and do another calculation to figure out how many moles of H2S would be produced. The molar ratio between S8 and H2S is that for every 1 mole of S8, which I'm writing down here because moles of S8 is up here, so I want them to be diagonal to one another. And just a reminder, the reason I'm doing that is because I want to cancel out moles of S8. I don't want that to be left around. I want it to disappear so that I'm only left with whatever unit is here, my unit of interest. 1 mole of S8 reacts to form 4 moles of H2S. So numerically, this is going to be 1.50 times 4, which is 6.00, and the units are moles of H2S. Hopefully this is starting to make some sense. So those were just a couple of examples of how to use simple molar ratios as a as a conversion factor to convert from moles of one substance to moles of another substance. I'm going to stop this video here and leave it at that, keep it kind of short and sweet, and leave some of the more complexities or some of the more complex things and the complexities to later videos. So I will see you in those videos. Until then, take care of yourselves. Peace out.